Hello everyone and welcome to the final chapter of this course. Woohoo! Chapter 9. In chapter 9 we're going to talk about sequences, series, and annuities. All right, so let's start right away with sequences and series. All right, our goal for this is to define and compute the sum a1 plus a2 plus a3 plus a4, and then notice that it keeps going, so of infinitely many numbers. All right. So section 9.1.1, sequences. In this section, we'll define the concept of sequences and study their limits. So when I say a sequence, what I mean is just an ordered list of numbers, real numbers. And so here, if I write it that way, what I mean is you take a 1, you plug in n equals 1, then you plug in 2, that's going to be the second, third number on your list, fourth, and so on. We're going to call each one a term. So the kth term of the sequence is AK. All right, so let's do an example. Consider the sequence. I have 1/2 to the n from n equals 1 to infinity. List the first 5 terms of this sequence and place them on the following graph. All right, so for n equals 1, I'm going to do n equals 2. I'm asked for 5. There you go. So for n equals 1, I have 1/2 to the 1. I have 1/2. So this is going to be n. This is going to be a n. So 1/2 right at the top. So that's a1. For n equals 2, I have 1/2 squared. That gives 1/4. So for 1 at n equals 2, I have 1/4. That's 25. So 0.25. That's a2. And I keep going. I have 1/8. Let's just do halfway from what we were, where we were. So A3 is here. And then every time we keep having it. So here it'd be 1/16, and we're getting an A5. It would be 1/32. All right, so it's different than a function because we're only plugging in the integer. So we don't have the curve that that is continuous and that you can draw without lifting your pen. All right, so but we have terms that keep going forever and ever, and so we could ask for a limit even though it's not a function. So evaluate the limit as n goes to infinity of an. So we want a limit as n goes to positive infinity, 1/2 to the n. If I just plug it in, I'll get 1/2 to the infinity. 2 to the infinity is infinity, and so I get 0. All right, so the limit of this sequence is 0 because you can see it in the graph as well. The terms are getting closer and closer to the x-axis, so closer and closer to 0. In the last problem, we used our knowledge of the function y equals 1/2x to find the limit of our sequence, right? I started talking about 1/2 to the something. The following theorem explains when we can do such a thing. All right, so if you have a function and you have a sequence, and let's assume that your sequence is really just a function evaluated at n. Okay, so here, for example, if I use 1/2 to the x, then an is 1/2 to the n, it's f of n. And so it would work in the previous case. If you know that the limit as x goes to infinity of f of x exists and gives you L, then the limit of an gives you L as well. This is called, by me, the Christmas lights theorem, right? Just by me. The reason I call it that is you have your, let's say you have your n-axis and you have your graph. So let me draw the graph in green. All right, so you have your graph. And let me say, let's assume that it approaches the level L here. Your sequence is not the whole red curve. It would be the value of the curve at each integer. So I like to think as the function as the electric cable and the sequence as the light bulbs that follow it along. If the cable is converging to a certain value, if it's going towards y equals L like it is in my picture, then the Christmas lights will also go to y equals L. All right, so let's try a few examples here. What if I have, actually let me leave that here, we might need it. The limit as n goes to positive infinity of arctan of n. We could replace that by arctan of x. And then we know that limit, that's one of the horizontal asymptote of arctan, that's pi on 2. All right, so the function goes to pi on 2. The sequence follows it along, also goes to pi on 2. All right, now if I plug in infinity into second limit, so into the limit of n over e to the n, I get infinity over e to the infinity. I get infinity over infinity. Now, I would like to use L'Hopital here. To use L'Hopital, I must look at functions. I cannot differentiate when I have just a bunch of Christmas lights, right? Can't calculate a derivative of these things. I need something that's at least continuous. And so what I'll do is I'll think of it as a function, which makes sense here. And then I'll take the derivative of top and of the bottom because that's what L'Hopital tells me to do. I'll get 1 over e to the x. I'll get 1 over infinity. I'll get 0. All right, so once you think of it as a function, you have the tools of the graphs that we know, the asymptotes that we know, and also you have L'Hopital that you can now use. All right, so let's try a couple more. This one, if I plug in, I get 1 plus 0. That's 1. And then the exponent goes to infinity. I have 1 to the infinity. That is one of the 3 exponential limits that are indeterminate. Yeah. All right, so I'm going to use L'Hopital again. So I'm going to call it L, and again, I'm going to think of it as a limit as x goes to infinity. And then I'm going to look at ln of L, just like we did in chapter 2. So that's going to be the limit as x goes to positive infinity, ln of 1 plus 1 over x to the x. I'm going to bring the x out of the log. And then I'm going to bring the x in the denominator. And now, finally, I can apply L'Hopital. I have log of 1, which is 0, over 1 over infinity, which is 0. And so I can take the derivatives. Derivative of 1 over x, that's x to the minus 1, so it's minus x to the minus 2. And then here I need to use the chain rule. So 1 over the interior times the derivative. Oh, sorry. Sorry. All right, so what do I get? I get 1 plus 1 over x minus x to the minus 2. Exactly the same thing underneath. These cancel. And so I get the limit as x goes to positive infinity of 1 over 1 plus 1 over x. That's 1 over 1 plus 0. That's 1. Don't forget, that's not the answer. That's log of the answer. So we apply the exponential to it. We get e to the 1, which is e. Final example here for this section. What if I have minus 1 to the x? Well, I can hear you say, why don't we just call it minus 1 to the x instead of minus 1 to the n? This doesn't exist. It only exists for integers and certain fraction. It doesn't exist in general. For example, if you write minus 1 to the 1/2, that's root of minus 1, and you could see how things will blow up. All right, so when you have a negative base, the powers are restricted because you can't take roots of a lot of negative numbers. So here we cannot use functions, but if we list the elements, you should see a pattern. So A1, that's -1. A2 is 1. A3 is -1, and so on. And A4 is 1, and so on. So really, if you want to draw it, you would get, sorry, start with a minus. You start with a minus, positive, minus, positive, and it doesn't get close, right? So we're not approaching a single value. And so this limit is D and E. It does not exist. All right, that's it for this video. See you next time.